When an autonomous robot rounds a sharp corner, the physical motion looks effortless, but underneath that movement is a complex chain of real-time calculations. To handle those calculations, developers typically rely on standard navigation frameworks, like ROS2's Nav2. These packages are incredibly robust, but they operate as massive, monolithic black boxes. They bring heavy computational overhead, and if a robot behaves unpredictably, isolating the exact logic failure inside that monolith can be extremely difficult. The alternative is constructing a bespoke navigation pipeline from scratch. By writing custom Python nodes in ROS2, we can bypass the standard stack entirely and build a highly targeted three-stage system. The core engineering challenge here is translation. We have to take a raw, static XY coordinate on a map and convert it into fluid, dynamically stable wheel rotation. Replacing a monolithic stack with modular nodes allows us to test each layer in perfect isolation. We control the exact math governing the robot at every single step. The system requires only two core inputs to function: a target destination coordinate and the robot's real-time physical location, pulled from the /AMCL pose topic. These inputs feed into a custom architecture of three distinct nodes: planner, smoother, and controller. Data passes left to right, intercepted and mathematically transformed at each stage. Finally, it exits as a /CMD val message, outputting the direct velocity commands that physically drive the motors. By designing this strict linear flow of data, we eliminate the unpredictability of a black box system. Every phase of the robot's motion becomes algorithmically transparent. The process begins at the first node in our pipeline, the informed A-star planner. Standard planners query thousands of pixels in an AMCL occupancy grid to find obstacles, consuming processing time. We skip the grid entirely. Because this robot operates in a fixed environment, we hard-code the walls directly into Python as simple 5-point geometric polygons. The algorithm treats these polygons as strict exclusion zones. It rapidly calculates the shortest, collision-free route from the robot's current position to the goal coordinate by navigating around these shapes. Once the route is calculated, the node bundles the coordinates and publishes them as a raw trajectory onto the /planned path topic. Swapping out a heavy, pixel-dense occupancy grid for a lightweight geometric obstacle map drastically reduces pathfinding latency. Look at the red path in this RViz output. The algorithm avoided walls, but because A-star uses a strict geometric grid, the output is sharp, angular waypoints. Following this directly demands an instantaneous pivot at every vertex, resulting in violent, jerky motion. Discrete geometric pathfinding creates mathematically valid routes, but those routes cannot translate directly to continuous physical motion. We need a translation layer. That translation happens in the second node, the path smoother, which subscribes directly to the jagged trajectory published by the planner. Many smoothing algorithms tie coordinates to time. Forcing a robot to reach a specific point at an exact second causes erratic speed variations as it struggles to maintain that arbitrary timeline. The solution is arc-length parameterization. Instead of time, this node measures the cumulative straight-line distance along the individual path segments. By mapping the waypoints based purely on how far the robot has traveled, we completely decouple the curve from time. Switching the mathematical foundation from time to distance ensures the trajectory remains perfectly consistent, regardless of how fast the wheels are actually turning. With arc length established, the node uses SciPy to fit two independent cubic splines, one calculating the continuous x-coordinates and one for the y-coordinates. Evaluating these splines across 200 uniformly spaced points produces a single, mathematically flawless curve. This RViz interface shows the exact result of that calculation. The raw, jagged red input is transformed and published to the /smoothed path topic as this continuous green trajectory. Mathematical interpolation bridges the gap between discrete grid constraints and the continuous reality of a moving vehicle. The final node is the Smart Path Controller. Operating at 10 Hz, it subscribes to that smoothed green path and prepares to move the motors. To track the curve accurately, the controller uses an adaptive look-ahead mechanic. When far from its destination, it projects a long target vector down the path. As the robot approaches its final destination, that vector dynamically shrinks, guaranteeing millimeter precision stopping. Simply chasing a point on a line often causes a robot oscillate wildly left and right. As shown in this control formula, we apply a PID-style angular damping term to the heading error, suppressing those oscillations before they reach the wheels. Finally, the controller analyzes the curve directly ahead. It automatically scales linear velocity, braking sharply into tight turns and accelerating smoothly through straightaways. Once the math settles, this final calculation is published directly to the /command-vel topic as raw linear and angular motor speeds. Adaptive look-ahead and angular damping successfully convert a static mathematical curve into fluid, responsive physical action. Because the planner, smoother, and controller are completely isolated ROS2 nodes, they have to be orchestrated to run concurrently. We use a specific ROS2 Python launch file, custom nav.launch.py, to spin up the entire architecture simultaneously with a single terminal command. Once launched, the nodes do not move the robot. They sit idle in the background, silently subscribing to their assigned topics, waiting for incoming data. The trigger arrives when an entirely separate perception node detects an event in the environment and publishes a final coordinate to the /goalpost topic. That single message instantly awakens the pipeline. The launch file acts as the binding agent, organizing 3 disconnected Python scripts into a unified, highly reactive robotic brain. In real-time execution, the cascade happens in milliseconds. A target is ingested. The planner maps a route, the smoother refines the curve, and the controller perfectly modulates velocity and heading to execute the curve. By shedding the opaque framework of Nav2 and building the math from first principles, we achieve a fully transparent autonomous system where every movement is explicitly defined, optimized, and controlled.